From the quiet solitude of our own world, we often look up, our eyes drawn to the pinpricks of light scattered across the inky canvas of night, each glimmer a distant sun, a potential system, a secret held in the vastness. But beyond the stars that populate our own Milky Way, there exists an object so magnificent, so monumental, that its very presence challenges our perception of home. It's a celestial titan, a spiral twin to our own galactic island, slowly but surely drawing closer with each passing moment. This is M31, the Andromeda galaxy, our closest large galactic neighbor, and the subject of one of humanity's most profound cosmic voyages of understanding. We are about to embark on a journey not just through space but through time, tracing the path of discovery that revealed Andromeda's true nature and the shocking implications it holds for our future. Prepare to voyage to M31 to unveil the secrets of our magnificent neighbor galaxy. For millennia, the faint fuzzy patch in the constellation Andromeda was little more than a curious smudge, an ethereal wisp observed by early stargazers. The Persian astronomer Abd al-Rahman al-Sufi, in his book of fixed stars around 964 AD, described it as a little cloud, an observation that would stand for centuries as an isolated curiosity. It was a hint, an almost imperceptible whisper from beyond, waiting for the right tools and minds to truly interpret its message. As telescopic astronomy began to blossom in the 17th century, astronomers like Simon Marius in 1612 were able to resolve it more clearly, though its nature remained stubbornly elusive. Charles Messier, cataloging celestial objects in the 18th century to avoid confusing them with comets, designated it as M31, an entry in his now famous list. But even with these early telescopic views, M31 was still largely understood as a nebulous cloud of gas and dust within our own galaxy, merely a component of the vast stellar tapestry that enveloped Earth. The true unveiling of M31 began with a slow, arduous process of questioning and observation. In the late 18th century, William Herschel, pushing the boundaries of telescope technology, began to discern individual stars within M31's outer regions. This was a crucial clue, suggesting it wasn't just a simple cloud, but perhaps a collection of stars too distant to be fully resolved. Yet, the dominant scientific paradigm of the time, championed by figures like Jacobus Kapteyn, still placed the Sun near the center of a comparatively small, self-contained universe. Effectively, our own Milky Way was thought to be the entire universe. M31, therefore, had to be a part of it. The idea of island universes, distinct galaxies existing independently of our own, was a radical, almost heretical concept. The stage was set for one of the most pivotal scientific debates of the early 20th century, the Great Debate of 1920 between Harlow Shapley and Heber Curtis. Shapley, based on his studies of globular clusters, argued for a vastly larger Milky Way, placing the Sun far from its center. But he maintained that M31 and other spiral nebulae were still relatively small gas clouds residing within our galaxy. His reasoning was partly based on the perceived immense energy required for them to be independent galaxies, and also on the lack of observed proper motion in M31, meaning it wasn't visibly moving across the sky, as would be expected of something very close but external. Curtis, on the other hand, a proponent of the island universe hypothesis, pointed to evidence of novae, exploding stars in M31 that were far fainter than typical galactic novae, suggesting they were incredibly distant. He also noted the presence of dark lanes within M31, similar to the dust lanes in our own Milky Way, hinting at a similar structure. The debate raged, fueled by limited data and immense conceptual leaps. It was a battle not just of observations but of cosmological philosophies. Was our universe contained within the bounds of our Milky Way, or was it just one of countless such stellar systems scattered across a truly boundless cosmos? The question of M31's true nature was the key to unlocking this monumental secret. The scientific community grappled with the implications if M31 was indeed an external galaxy. It would mean the universe was far, far grander than anyone had previously imagined. The very concept of our universe would expand exponentially, rendering humanity's perceived central place in the cosmos even more insignificant. The ultimate breakthrough arrived with Edwin Hubble, armed with the 100-inch Hooker telescope at Mount Wilson Observatory. In the mid-1920s, Hubble began meticulously studying M31, searching for specific types of stars known as Cepheid variables. These pulsating stars have a crucial characteristic: their Pulsarian period is directly related to their intrinsic luminosity, meaning how bright they truly are. By comparing their intrinsic brightness to their apparent brightness as seen from Earth, astronomers can calculate their distance. It was a cosmic measuring stick, precise and reliable. Hubble painstakingly identified Cepheid variables in M31, and what he found was nothing short of revolutionary. The Cepheids in M31 were incredibly faint, far fainter than any Cepheids known to exist within our own Milky Way. This wasn't because they were intrinsically dim stars, it was because they were unfathomably distant. His calculations placed M31 not merely tens of thousands of light years away, but over 1 million light years away, a distance so vast that it unequivocally positioned M31 far outside the boundaries of our own Milky Way galaxy. It was a separate, colossal island of stars, a galaxy in its own right, just like ours. This single irrefutable observation dissolved the great debate, forever changing humanity's understanding of the universe. M31 was not a nebula within our galaxy, it was an independent, majestic neighbor, and its existence proved that the cosmos was filled with countless galaxies, each a universe in miniature. This revelation was a profound shift in human perspective, moving us from a geocentric universe to a helioscentric one, and then with Hubble's discovery, to a galactic one, where our galaxy is but one among billions. The ancient little cloud had revealed its true, shocking scale, paving the way for an entirely new era of cosmic exploration and existential contemplation. M31 was no longer just a smudge, it was a beacon, inviting us to contemplate the true scale of our cosmic home. The revelation of M31 as an independent galaxy opened a new chapter in astronomy, transforming it from a distant smudge into a subject of intense scientific scrutiny. With its true distance established, astronomers could begin to piece together its intricate structure, a cosmic tapestry woven from billions upon billions of stars, gas clouds, and dust. Andromeda, it turns out, is not merely a twin to our Milky Way, it is a grander, perhaps even more ancient sister. Spanning an estimated 220 light-years across, it dwarfs our own galaxy's roughly 100 light-year diameter. Its sheer scale is difficult to grasp, containing an estimated trillion stars, more than twice the number in the Milky Way. Imagine a celestial city not just sprawling but teeming with life-giving suns, each a potential stage for worlds yet undiscovered. Beyond its imposing size, Andromeda presents a breathtaking spectacle of cosmic architecture. Like our Milky Way, it is a spiral galaxy, though its spiral arms appear more tightly wound and less clumpy than ours, these arms spiraling outwards from a brilliant central bulge, are regions of active star formation studded with hot young blue stars and glowing nebulae where new suns are still being born. Yet deeper observations have revealed a peculiar dual structure within Andromeda's core. Instead of a single bright nucleus, it possesses two distinct bright concentrations, a phenomenon that initially baffled astronomers. This double nucleus is now understood to be a consequence of a past galactic encounter, likely the remnants of a smaller galaxy that Andromeda cannibalized long ago. Its core now orbiting the larger galaxy's central supermassive black hole. This black hole, Sagittarius's larger cousin, is estimated to be over 100 million times the mass of our Sun, a silent, powerful gravitational anchor around which an entire galactic empire revolves. As we probe deeper into Andromeda's mysteries, the subtle whispers from its colossal halo begin to reach us. Speaking of something far more enigmatic than stars and gas, dark matter, this invisible, mysterious substance, undetectable by conventional means, is believed to make up roughly 27% of the universe's mass energy content. We cannot see it, but we can detect its gravitational influence. Andromeda, like all large galaxies, is encased in a vast, sprawling halo of dark matter that extends far beyond its visible stellar disk. This dark matter provides the gravitational scaffolding that holds the galaxy together, preventing its rapidly rotating outer stars from simply flying off into intergalactic space. Without it, Andromeda, and indeed the Milky Way, would simply tear themselves apart. What makes Andromeda's dark matter distribution particularly intriguing is its implications for galaxy formation models. Recent highly precise measurements of M31's rotation curve, the speed at which stars orbit the galactic center at various distances, have allowed scientists to map out its dark matter halo with unprecedented detail. These studies suggest that Andromeda's dark matter halo is not perfectly spherical or uniformly distributed. Instead, it exhibits subtle irregularities, perhaps even warps or elongations, which could be telltale signs of past gravitational interactions with other galaxies or even remnants of dark matter from consumed dwarf galaxies. Understanding these nuances in Andromeda's dark matter structure provides crucial data points for refining our cosmological models, helping us to better understand how galaxies like ours form and evolve within the larger cosmic web. It's like finding a subtle fingerprint, offering clues about its deeper unseen history. But beyond the grand structures and the invisible scaffolding, Andromeda continues to surprise with its hidden stellar anomalies. Even in a galaxy of 1 trillion stars, some stand out as cosmic enigmas, defying our conventional understanding of stellar evolution or galactic dynamics. For instance, astronomers have discovered populations of ultra-compact dwarf galaxies orbiting M31 that are far more numerous and massive than initially predicted. These are tiny but incredibly dense clusters of stars, some appearing to be stripped-down cores of much larger galaxies that Andromeda has consumed over billions of years. Their existence provides direct evidence of galactic cannibalism, a brutal but essential process in the growth of large galaxies. It paints a picture of Andromeda not as a serene, isolated island, but as a hungry giant, constantly absorbing smaller companions. Furthermore, within Andromeda's vast stellar disk, observations have revealed strange, dislocated streams of stars that don't follow the typical galactic rotation. These stellar streams are like ghostly trails left behind by smaller galaxies that have been tidily disrupted by Andromeda's immense gravity, stretched and torn apart into long flowing ribbons of stars. Studying these streams is akin to forensic astronomy, allowing scientists to reconstruct the violent gravitational encounters that shaped Andromeda over cosmic temescals. One particularly prominent feature is the giant stream, a vast structure extending for hundreds of thousands of light years, believed to be the remnants of a dwarf galaxy that was ripped apart by Andromeda approximately 2 billion years ago. These stellar ghosts are not merely curiosities, they are living laboratories, providing direct evidence of galactic interactions and the dynamic, sometimes violent nature of galaxy evolution. Even more intriguing are the peculiar behaviors observed in some of Andromeda's globular clusters. While most globular clusters are ancient, spherical collections of millions of stars, some in Andromeda exhibit unusual characteristics. For example, a subset of its globular clusters appears to be much younger than the galaxy itself, suggesting they might have formed after a major merger event, perhaps from the gas and dust disturbed by the collision. Others show evidence of containing intermediate mass black holes, objects whose existence bridges the gap between stellar mass black holes and the supermassive giants found at galactic cores. These anomalies challenge our assumptions about how star clusters form and evolve, pushing the boundaries of our understanding of stellar dynamics within such a colossal system. Each new discovery, each unexpected observation, adds another layer to the complex unfolding story of Andromeda, reminding us that even our closest galactic neighbor holds secrets waiting to be unveiled. As we have traversed the cosmic expanse from Andromeda's initial recognition as a faint smudge to its unveiling as a galactic titan teeming with untold stars and hidden dark matter, one final profound truth awaits: the ultimate destiny of M31 is inextricably linked with our own. For billions of years, Andromeda has been moving towards us, its gravitational pull subtly but inexorably drawing our Milky Way closer. Unlike the vast majority of galaxies in the universe, which are receding from us due to the expansion of space, Andromeda exhibits a blue shift, meaning its light is shifted towards the bluer end of the spectrum, indicating it is approaching. This isn't a mere statistical anomaly, it is a cosmic inevitability. We are on a collision course, destined to merge with our colossal neighbor. Current estimations, refined by precise measurements from the Hubble Space Telescope tracking the proper motion of stars within Andromeda, indicate that the two galaxies are hurtling towards each other at approximately 110 kilometers per second, or about 246 miles per hour. This cosmic encounter is not an event for tomorrow, or even a million years from now. It is projected to occur in roughly 4.5 billion years, a timeline so vast that it dwarfs the entire history of life on Earth. By then, our sun will be well into its red giant phase, expanding to engulf the inner planets, rendering Earth uninhabitable long before the galactic grand waltz begins. But the merger itself will be a spectacle of unimaginable scale and grandeur, reshaping the local universe and creating a new cosmic entity. It's crucial to understand that this galactic collision will not be a sudden destructive impact like two cars crashing head-on. The vast distances between stars are simply too immense for that. If the sun were a grain of sand, the nearest star, Proxima Centauri, would be miles away. A galaxy is mostly empty space. Instead of direct stellar impacts, what will occur is a slow, graceful, yet powerfully disruptive gravitational dance. As the two immense spiral galaxies approach each other, their gravitational fields will begin to distort and pull at one another. The spiral arms, those elegant structures of gas and dust, will be tugged and stretched. Like taffy pulled by an unseen hand, tidal forces will rip through the disks, scattering stars from their familiar orbits and igniting new bursts of star formation as gas clouds collide and condense. The process will unfold over hundreds of millions, possibly even billions of years. First, the two galaxies will perform a series of near misses, passing through each other like ghostly apparitions. Each pass will exert a stronger gravitational influence, slowing their relative motion and gradually winding them tighter. Stars will be flung outwards into vast tidal tails, forming new streams of light across the merging chaos. Eventually, the two central supermassive black holes, the 4 million solar mass black hole at the heart of the Milky Way and Andromeda's 100 million solar mass behemoth, will begin their own gravitational dance. They will spiral inward towards each other, emitting powerful gravitational waves as they draw closer, until they eventually coalesce to form a single, even more massive supermassive black hole. This final merger of the central engines will mark the true birth of a new galaxy. The resulting celestial leviathan will be a grand elliptical galaxy, a sprawling amorphous blob of stars rather than the familiar flat spirals we inhabit today. Scientists have already given this future galaxy a provisional name, Andromeda or Andromeda. Its stars will be redistributed into new chaotic orbits, no longer confined to a neat galactic plane but swirling in a vast three-dimensional ellipsoid. The nebulae and gas clouds that fueled star formation in the spiral arms will largely be consumed or dispersed, leading to a much lower rate of new star birth. The combined dust and gas will likely experience a final intense burst of star formation during the merger's most active phase, creating a generation of young blue stars that will illuminate the newly forming elliptical core before fading over time. For any hypothetical observers in a distant future who might witness this cosmic ballet, the night sky would be transformed beyond recognition. Initially, Andromeda would grow steadily larger in our sky, its features becoming visible to the naked eye with breathtaking detail. Then, as the merger commences, the heavens would become a canvas of cosmic fire, with stellar streams arcing across the sky and new nebulae flaring into existence, and the two galactic cores merging into a dazzling display of light and gravitational chaos. Eventually, the spectacle would subside, replaced by the serene, majestic expanse of Andromeda, a testament to the dynamic, ever-evolving nature of the universe. Our familiar spiral home, the Milky Way, would cease to exist as a distinct entity, its identity subsumed into something grander and more ancient-looking. This inevitable collision is not just an astronomical curiosity, it is a profound testament to the fundamental processes that shape the cosmos. Galaxy mergers are not rare events, they are the primary drivers of galactic evolution, leading to the formation of the largest and most massive galaxies in the universe. Our journey to M31, from its discovery as a little cloud to the understanding of its impending embrace with our own galaxy, is a story of continuous revelation. It pushes us to contemplate not just our place in the vastness, but our role within a cosmic narrative that stretches billions of years into the future. It reminds us that nothing in the universe is truly static. and that even the grandest structures are subject to the ceaseless powerful forces of gravity and time. The voyage to M31 is in essence a voyage to our own cosmic future, a future where two galactic titans become one, forever altering the landscape of our local universe. The knowledge we've gained about Andromeda, this majestic celestial neighbor, has not only deepened our scientific understanding but has also quietly expanded our imagination. We've peered through the veil of cosmic dust and time, deciphering the whispers from a trillion stars, unraveling the invisible embrace of dark matter, and tracing the paths of ancient galactic cannibalism. Our journey through its past and present has laid bare the astonishing tapestry of its existence. And now, as we contemplate the inevitable union with our galactic twin, the universe reveals another layer of its profound interconnected nature. The thought of two entire galaxies, each a sprawling island of billions of suns, gracefully merging into a single colossal entity might seem overwhelming. Yet it is a testament to the subtle, powerful dance of gravity that has choreographed the cosmos for eons. As we look up at the night sky, M31 remains a beacon, a gentle reminder that our existence is part of something far grander, a continuous unfolding story of cosmic evolution. Its light, traveling for millions of years to reach our eyes, carries whispers of a shared future, a future where our descendants, should they endure, might gaze upon a single magnificent elliptical galaxy, born from the intimate embrace of two colossal spirals. The universe continues its quiet work, shaping and reshaping, always moving, always becoming.